You clicked on this video because you heard about world models and want to know what they actually are right now. The reality is far less magical than the hype suggests. These systems are not universal physics engines waiting for activation, but specialized next-token predictors trained on massive temporal datasets. By the end of this explanation, you will understand why your current hardware strategy based on raw memory capacity is fundamentally misaligned with how these models actually function and what specific architectural shift is required to make them viable in production environments. The term world model has become a catch-all phrase that obscures more than it clarifies for anyone trying to build or deploy this technology today. When researchers talk about world models, they often imply a system capable of simulating every possible future state with high fidelity. This implies a causal understanding where the machine knows how gravity works independently of having seen an object fall before. The truth is that current architectures do not operate through true simulation, but rather through statistical interpolation. They predict what comes next based on the likelihood of sequences observed during training, not because they have internalized universal laws of physics. This distinction creates a critical gap between expectation and reality for software engineers entering this field. You might design your system assuming it can handle any physical configuration or environmental change without retraining. In practice, these models fail catastrophically when faced with new hardware embodiments that differ from their training distribution. This phenomenon is known as the hardware lottery in robotics research. A model trained on a specific quadrupedal robot will often overfit to the kinematic properties of that exact machine. If you move it to a different platform or slightly alter its mechanical structure, performance collapses because the statistical patterns no longer match reality. The root cause lies in how these models process information during inference. Unlike standard large language models where compute power is the primary constraint for generating text tokens, world models face a unique bottleneck related to memory access patterns. They require continuous streaming of high-dimensional temporal data to simulate future states effectively. This creates what engineers call a memory wall situation, where the speed at which data can be fetched from memory limits performance more than the raw number of calculations available on the chip. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider how standard GPUs are optimized for massive parallel computation with large amounts of video random access memory. These designs assume that once data is loaded, it can stay in cache while thousands of operations occur simultaneously. World models break this assumption because they must constantly fetch new frames and state vectors to predict the next moment in time. The architecture demands rapid retrieval rates rather than just storage capacity. This means high-bandwidth memory becomes far more valuable than raw gigabytes of VRAM for these specific workloads. Recent research into morphology-conditioned world models offers a glimpse at how we might address this generalization problem without sacrificing performance on individual embodiments. Scientists have found success by explicitly encoding engineering specifications directly into the model during training rather than expecting it to learn physical properties implicitly. This approach allows systems to achieve zero-shot generalization across different quadrupedal robots, effectively making them hardware-agnostic within a defined distribution of mechanical designs. However, this solution introduces its own trade-offs that every practitioner must weigh carefully before committing resources. The explicit encoding process alters the entire training pipeline and prioritizes broad applicability over peak performance on any single machine type. You gain flexibility but lose some efficiency in specific scenarios where you could have squeezed out higher accuracy by focusing exclusively on one robot design. This is a fundamental production decision that determines whether your system remains a specialized tool or attempts to be a general-purpose reasoning engine. The hardware implications of this architectural reality are profound and often overlooked by teams purchasing infrastructure based on traditional benchmarks. Achieving the necessary temporal resolution for actionable reasoning requires memory bandwidth capabilities that current GPU clusters simply do not provide efficiently in their standard configurations. You cannot solve a bandwidth bottleneck just by adding more cards if those cards remain limited by how fast data can move between processors and memory banks. The limiting factor shifts from compute to throughput, rendering high-capacity GPUs inefficient for the continuous streaming demands of autoregressive temporal generation. This creates a significant mismatch in the current market, where developers buy expensive hardware optimized for capacity while their models starve for bandwidth during inference. Until this architectural gap is closed through dedicated memory subsystems or new chip designs that prioritize data movement over raw compute density, world models will remain confined to narrow domains rather than achieving the broad utility often promised by industry leaders. The field currently lacks standardized benchmarks that measure simulation fidelity versus simple prediction accuracy, making it difficult for practitioners to validate claims about true generalization capabilities in real-world deployments. Recognizing this fundamental shift from capacity-focused to bandwidth-focused hardware requirements changes how you approach building these systems entirely. You stop asking, what is the largest model I can fit on my cluster, and start asking, where does data movement become the bottleneck in my pipeline? This perspective forces a reevaluation of every component in your stack, from storage layers to network interconnects, ensuring that the infrastructure supports the specific temporal streaming needs of next token prediction rather than just providing space for static weights. The path forward requires accepting that these models are not universal simulators, but specialized interpolators, bounded by their training distributions and hardware constraints. Success comes from aligning your architectural choices with this reality, rather than fighting against it in pursuit of an idealized simulation capability. By focusing on memory bandwidth optimization and explicit morphology conditioning, you can build systems that generalize effectively within defined parameters without falling into the trap of overpromising universal physics understanding. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.